for Scott's second lecture on homogenization.
So for this hour, I will try to explain a little bit how the answer to the question in the back of the room about how we would quantify homogenization. So there are lots of ways that you can choose to quantify homogenization. There's lots of different methods. So I'm going to be presenting the one that I know best, which is based on the stuff I did in the last hour. So as opposed to the stuff I did yesterday, it's more based on the sort of energy variational approach. Okay. Before you can really talk about quantitative stuff, you have to talk about quantifying the probability measure in a better way than we have done so far. So far we've said if the probability measure is just stationary, we can prove some homogenization, but then the limit is not even a constant and so on. So if you make the probability measure ergodic, then the homogenized matrix is at least deterministic. It's a constant, not a random variable. But you can't get a rate for that limit because the ergodic theorem can have an arbitrarily slow rate. So unless you assume more, you don't get more. Okay, you make a soft assumption, you get a soft conclusion. So we have to talk about this. This is really unpleasant. I'm sorry, but you have to talk about how you're going to quantify the probability measure or the ergodicity of the probability measure. Okay, so now the problem when you quantify the ergodicity of the probability measure is that it's distasteful. What is the right assumption to choose? Right, so there's a whole spectrum of assumptions. There's like more assumptions than there are like different kinds of beetles in Brazil. So you want to like pick the assumption that, so I mean, you basically have two choices. You can try to pick the most general assumption, but that's kind of ergodicity. So the most general assumption under which you can prove things, or you can try to make a whole family of assumptions that covers every possible case. But as soon as you do that, someone's going to come and say, haha, but you don't cover this case. And that must be a limitation of your proof, right? So, or you can say, I choose the most specific case, which is what's usually done in statistical mechanics. And that's just you assume independence. So what would the assumption of independence? So one choice is that you can assume independence. In statistical mechanics, usually these kinds of problems are put on a lattice, not in the continuum. And you zoom out and make the lattice really small, and you get a limit in the continuum. And because you have a lattice, when you assume independence, there's countably many points or edges or something. And so you can just assume the whole ensemble is independent. But for us, we have these measurable coefficient fields, which are in the continuum. And so assuming independence is a bit more technical, because if you try to make it independent any two distinct points, you can't even make the thing measurable. Okay. So this is kind of a stupid thing to worry about. You could just do the discrete problem or whatever, which is fine. But the standard way to do it is to assume finite range dependence. Okay, so finite range dependence is, I think, the strongest assumption that you can reasonably make, I think. And the way that it works is, okay, I have to talk about sigma algebra again for a second in order to formalize this. So yesterday I had this sigma algebra capital F, which was like all of the measurable, the list of a list of random variables that should be measurable. And now I'm going to restrict it to a given domain. So it's the sigma algebra generated by kind of events when I restrict to capital U. So let's say the random variable would be A maps to integral over U of A against phi of x dx for some phi. Okay, so I'm gonna make my sigma algebra be the set of things which make this measurable. Now notice that because and U is a given domain, okay, it can just be any Borel set. Okay, so this gives me an F sub U. If U would be RD, I would get the same F I had before. And if I have a smaller U, then I'm only, it's a smaller sigma algebra because it only looks at, the set of events that only depends on U in a smaller domain U. Okay, I can't, if I tried to make a random variable, like what is A doing outside of U, this sigma algebra just wouldn't know. Okay, so then independence would be or finite range dependence would be that the distance, if you have two Borel sets and the distance is bigger than one, just the normal Euclidean distance, this would imply that these sigma algebras are independent. Okay, so this is if you want I think the closest that you can get to the typical assumption in statistical physics of IID on the lattice. And you can actually, there's not, I mean, you can do this whole homogenization theory that I'm doing instead of equations in the continuum. You can just put it on the lattice directly and just do the whole theory for that. And it doesn't simplify or complexify anything. It's just the same. You just have to use, you have to change your notation in appropriate ways. Make sure that, your derivative is a finite difference, but none of the proofs are made any more complicated. It is annoying that boundaries have now have a positive volume, but that's the only kind of irritation. Anyway, so this is one thing that you can do. This is not super general, but it's super specific. You can also, what's also done traditionally is you can assume there's some decay of correlation on, you can write something like this with a decay of correlation, or you can say your A of X can be approximately finite range dependent. So you could say A of X is the sum of a bunch of A's, for example, something like this. Okay, where, so here, this is just an example, AI in L infinity is bounded by 2 to the minus I, and AI has range of dependence 2 to the I. Okay, I don't know. You could be you could handle that case even though it has infinite range of dependence. Okay, so you can kind of if you perturb off of this assumption, you can do things. There's another. So there's the other set of assumptions which you can do is you can assume your probability measure satisfies a functional inequality or concentration inequality. So this idea was first brought up by Nadaf and Tom Spencer, who took their inspiration from the Braskamp-Leib inequality, basically, in statistical physics. And they said, you can make the same assumption on your, if you're, like, for example, if your A of X was a random checkerboard. So then it kind of becomes a discrete thing, even though it's in the continuum. The checkerboard squares are in the continuum, but you kind of have a discrete probability space. With that kind of assumption, you can prove, if you assume a functional or concentration inequality on your probability space, then you can also prove homogenization results. Okay, so these are the sort of two kinds of sets of assumptions that one can make. And you can sort of develop the theory in parallel using one or the other. Okay, so I like this one. Tuomo and Jean-Christophe and I like this one. Julian likes this one. So it depends on your taste. So I'm going to sort of talk about this one. Tuomo and I are writing a survey in which we make a super general, assumption just to flex that does them both at the same time, so that we don't get accused of only being able to do the finite range dependence case anymore. Okay, so it's possible to put all of this into some horrible general assumption. It doesn't really change the proof too much, except you have to keep going back in the document and trying to remember what the definitions are because it's complicated, but it's possible to do it. Okay, so anyway, but let me go ahead and do this one unless anyone objects. So I'm going to just do independence, which is the sort of strongest assumption that I can make and still have something random. Okay, any questions about that? So now let's talk about what we expect to show. Okay, so remember that our goal here is to understand the correctors eventually. Let's just say that's the goal. Okay, and in particular, we would like so this family of guys. And we would like to understand what these guys do at large scales quantitatively. Okay, so the correctors satisfy this equation. So I write the of X here to emphasize this is in the whole space. So remember it's set in the whole space. So okay, and this sort of uniquely defines the phi after you say that it's the expectation of its gradient is 0. So expectation of its gradient is 0. This really means you take the expectation after you integrate over a unit cell. Okay, so let's say that I have that. Now, how am I going to understand the phi, right? So your question was, if you assume some independence on the A, can you get independence on the phi? Or, can you say something about the phi? So we will assume now that the probability measure, which gives us the A, has finite range dependence. Did I write this? Yeah, okay, so I didn't say. So assume P has finite range dependence, or unit range dependence, really. The range of dependence is 1. Okay. Okay, so how are we going to understand the question is how to get the quantitative ergodic information from P from A to the phi. Okay, and the problem, besides the fact the blackboard keeps falling down, is that the A may have finite range dependence, but the phi does not. Even though the phi, you can think of the phi, of course, in some sense as a function of the A, but it's not a local function, right? So phi at a point x depends on A of x everywhere. So the problem. So how are you going to use independence? Okay, so yeah, again, there's various ways to answer this. Yes, please.
Sorry, last time I thought that you defined something like phi of m or something like that because you defined.
Yes, I mean, yeah. So I could rephrase the question about phi of m.
Okay.
It would be the same. It would be the same level of difficulty. Yeah.
Okay. It's just because I'm not completely sure that phi. I believe that phi exists, but phi of m is more clear to me that it's.
Yes. No. You're right. Phi of e is some abstract nonsense that doesn't really exist, and phi m exists. That's correct. Yeah. Yeah. If you complain that if you insist on this, I mean, it's kind of like yeah. It's like. Anyway, I won't say that. But this is really some sort of this is some infinite blowdown limit or something like that. And you don't. What's happening very, very far away at infinity, it doesn't matter if you're looking at any finite region. Again, I don't really believe that limits are real. Right? For me, like they're like the limit t goes to infinity. That's not really real. What's real is t is 10 to the 20, and your thing is small, right? Okay, so that's right. So we're going to actually put this, sort of on a finite domain, and we're not going to ask the question then about the correctors. That's actually kind of an inappropriate question to ask. Like, what is this corrector doing in a bounded region? We should sort of look at the solutions in that bounded region and look at them together and try to figure out what's happening. So another talking point that you could say is, we're not going to look at one solution and try to homogenize it. We're going to try to homogenize the whole equation that is the coefficient field. Okay, so this is the point of view. So how are we going to do that? Well, we're not going to study the solutions directly. We're going to study the sort of coarse-grained coefficient field. So what I did in the last talk is, you remember that I defined this thing. I feed a domain into my coefficient field, and that looks. You have to get used to that notation, but this is supposed to be the coarse-grained field in this box. So this is the A of x coarse-grained with respect to this box. Okay, and so if you want, so here's my, it's hard. I'll try to draw a cartoon. Okay, here's a very, very, very big box. Okay, it's not infinite because there are no infinitely large boxes. Not really. Okay, so you can cut this into little cubes. By the way, it goes both ways. If you have a big box, you shouldn't worry about point-wise information or what's happening on scale 1. That's also stupid to do, or you shouldn't do that. you should only worry about the scales that are near your scale, right? The picture is somehow there's something evolving as you move across the scales. And what happens on scale 1 should not really talk to what happens at scale 10 to the 25. Okay, so let's say that you're on the scale of these little boxes and you've computed this A of this, and you know, each little box may be a bit different. Okay, so each of them has like a value of A. You know, I mean, I would like to use colors that are almost the same color but slightly different, you know, kind of like a, okay, but so like imagine this is colored in colors and they're all like a slightly different shade of red. Okay. Now that means that you're at kind of a large scale and the A of the thing is starting to converge. At infinity, it'll converge to a constant, like the A of RD is A bar, okay? But at any given scale, it's not converged, and you have kind of a random Corson coefficient field at that scale. And what you'd like to do is now forget about the information below that scale and just say, okay, I'm going to homogenize this big box as though these small boxes were the coefficient field and sort of average them the way that I averaged the coefficient field to get the A of that box. Okay, so you want to pass information up the scales and never look below the given scale that you're at. If you try to look like at a scale too small, if you're doing that in your proof, you're gonna, you know, it's not that it'll never work, but you know, it's probably not going to be super robust. You'll be able to, you know, your proof will break if you change the assumption slightly and so on. Okay, so you want to really only go scale to scale. So, and so this is what we would like to, okay, so now I go back to when I was speaking of A bar. We think of A bar as some nonlinear average of the coefficient field, and I proved these inequalities. I proved that it's below the average of A, and it's above the harmonic mean of A. Okay, so it's kind of between two averages of A. I don't know what it is. It's some nonlinear averaging of the whole coefficient field, right? It's like you've got to know the whole coefficient field, A of X, to understand A bar. But we know it's between these two things. So you could imagine that as this starts to converge to a constant, this Corson field, these will all be very close to each other, and you'll very rarely have a cube with a different value from the other cubes. Like their fluctuations will be kind of small. Well, if you're between, and let's say we knew that the Corson coefficient field in the bigger cube satisfies these bounds with respect to the smaller cubes, okay? Then you would know that because the variance is small, that you're stuck between two different averages. So you're actually equal to both of them up to the square of the fluctuations, okay? And in a way, you'd be linearizing the problem. These bounds say that up to a quadratic error, at first order, A bar is the average of A. Okay, so let me say that a bit differently. So if your coefficient field, so I'll just say it like this. If your coefficient field, for example, minus the identity L infinity, if you knew that this was small, that you were in some small contrast regime, then you would know that the A bar, okay, you would know that the A bar is also close to the identity up to delta. That's obvious, but you'd know better. You would know that it's the average of A up to delta squared. Okay, so your nonlinear problem is becoming a simple average. Now, if we could do that in this case, that would be super nice because our simple averages, you know, like I know how to get sort of averages to contract. That's just use some IID random variables. I can do, like even I can do that. Okay, so in this, if you are transferring the ergodic information from A to phi at this level, then it doesn't matter what mixing condition you have because any mixing condition can do that. I mean, if you, like, there's a lot of mixing conditions, but none of them fail on linear. You know, if your mixing condition doesn't satisfy a linear concentration inequality, then it's probably not right to call it a mixing condition. Okay, so we're going to use independence, but we're only ever going to apply the ergodic theorem or whatever to sums of random variables which are local, and therefore, you know, we can't be beat when it comes to the general mixing conditions that you could use. Okay, so this is the intuition of what's going to happen, is that we're going to sort of iterate up the scales, and we're going to see that there's some quadratic square that appears that allows us to accelerate the rate of convergence and see that the coarse grained field is going to behave like white noise, even though the solutions are going to be having correlations. And so you can study the coarse grained field, see that it's white noise, and then get the information for the solutions as a corollary. Okay, so the point is that you should focus on this. Okay, and I think DeGiorgi kind of understood that in 1973.
Scott, can I ask you a question?
Yes.
The thing you're talking about over here, you're saying there's like a separate argument to do this. You're not saying that the average and the harmonic average are within delta squared of each other, right? Because I guess
I'm saying if this, yes, if A oscillates, these are within delta squared. The harmonic mean, if you linearize it, is the mean, and there's a delta squared. I mean, look, I can draw the graphs. The graphs are tangent when the thing's constant. I mean, they give the same answer when it's constant, right? So the two graphs, yeah, I mean, it's I don't okay, I don't, but yeah, they're actually tangent and they're equal. I mean, any definition of mean will usually be the same as the normal mean in small contrast up to delta squared. Yeah. And so we're, in a sense, I mean, the way that we're going to view this is we're flowing, it's like it's a convergence to equilibrium. We start on a small scale. We're very far from equilibrium. As we go up the scales, we get closer and closer and closer. And once once you're close enough to equilibrium, you can linearize, right? It's like how you prove convergence in a nonlinear problem. You have some method to get yourself into the linearization regime. And once you're close to being the equilibrium, like you're close to homogenized or whatever, then you can linearize and use estimates for the linearized equation. My equation is linear, but what I'm talking about is the kind of the way that the A bar depends on A of x. That's nonlinear. So I'm viewing it like that. Okay, I'm sorry this is too much blah blah with no specifics, but it's difficult to explain the philosophy without the proof, but then the proof is some mess, and it's hard when you see the proof to understand the philosophy. So it's kind of a problem to explain. Okay, but this is what I'm, yes. That you may wonder is, do my coarse grain coefficients satisfy this? Do they satisfy those bounds in the coarse grain way? Because if they did, then you could wait until the sub-additive ergodic theorem has made them close at some scale. And then you could apply them and like you square the error at every scale and you're in good shape. So do they? Well, this one is just exactly sub-additivity. And so if you had this one, you'd be really happy. But that's false. So at this point, you can just give up. Because the sub-additive coarsened, the coarsened coefficient field does not satisfy that. That's really bad. Okay, before I tell you how to fix that, so let me tell you what should be true about so we believe that the coarse grain coefficient field, whatever that means, is going to converge to white noise. I'm going to try to explain that. What do the solutions converge to? So let's look at the correctors like this. Okay, so we have this equation. And I'm going to use the same philosophy that I can kind of ignore quadratic errors. Okay, let's go ahead and assume that my A is in this situation. Okay, so I'm going to assume that my A of x is literally small contrast, but I'm actually going to do this proof literally, but after I've coarse grained. So the proof I'm doing is not a lie. It's going to be actually done. But for now, we're just going to assume that we're literally in the small contrast case, so we don't have to do anything to get there. We can just linearize at scale 1. Okay, so what I'm going to do then is I'm going to write this equation like this. A bar grad phi. I'm just going to change the A to A bar because I prefer it. And then I'm going to write the right-hand side. And then I'm going to add the error that I made when I did that, which should be divergence of, okay, so now there's a 50-50 chance I get the sign right. Grad phi. Is that right, Jean-Christophe? Okay, good. Jean-Christophe is fixing those typos today. So this one we're assuming is O of delta. And you can convince yourself that if you're in this regime, it means that the correctors actually have to also be O of delta. So this one should also be O of delta. So this is O of delta squared. Okay, so let's imagine that there's a way to just forget about that. Now we have a much nicer equation because the operator is not random. The only randomness is in the right-hand side. And I can write a Green's function formula for this, right? I can just write a convolution formula. But actually, are there any probabilists here? No? Do you know what this is? Like if you have, so this is basically like Laplacian. You have Laplacian say W equals divergence of a vector field F, and F is white noise. This is a very famous object in probability. Do you know what it is?
You're asking me.
Just any probabilist. So what is this? This is the Helmholtz projection of white noise onto the potential fields. Like you have white noise, but white noise is not the gradient of anything, right? Because you can go in a loop and there's no reason why it'd be zero. So you'd like to make it a potential field. So you project it on the space of potential fields. What do you get? You get the GFF. So this is the way that you should define the GFF instead of that Fourier stuff. Just spread the word. Yeah, the Gaussian free field. Okay. Loop soup. Loop soup is like a differential form Gaussian free field, right? That's over my head. Free field. Okay, so there's some fancy name for what the limit of the corrector should be in the sense of distributions, and it's called the Gaussian free field. And what it basically means is that it's a very particular Gaussian field. What it means is that if you take the corrector and you have like a nice test function here, and you multiply and you, let's see, what should I do? I should spread the test function out like this, so that it's. Did I do that right? Yes, I did it right. So this says like L1 norm of order 1, say, or equal to 1, and I'm spreading this out on the scale R. Okay, and I'm multiplying by this field, which I know has mean 0. And if this would be the Gaussian free field, then I would know that this is of size R to the minus D over 2. And I would not only know its size, but I would know that it converges actually, if I multiply by R to the D over 2, so I divide by its size, now it's of order 1, and I can hope that it converges to something, and it'll converge to a normal random variable with variance that you can compute from the eta, and variance in terms of eta. So it's like having a central limit theorem for your random field, but you understand the whole covariance of the random field because you can vary the eta. Okay, so this is what you actually end up proving in this theory, is that you do prove that the correctors converge to the Gaussian free field after you rescale it properly. Okay, so I won't prove that though in the class by the end of this hour. Okay, any questions about that? No. Okay, so I'm going to try now. So this comes out as a corollary of the fact that the coarse grain coefficient field converges to white noise. So we instead prove that the coarse grain coefficient field, whatever that means, it's vaguely this thing, converges to white noise, and we get this GFF as like a corollary, because it's just, you can think of the Gaussian free field like that. Okay, so the way that this works is you can't just quickly in a few pages prove this super specific result. Okay, I mean, after all, even proving that this thing is converging to is little o of 1 is homogenization. So if you put r to the minus d over, if you want to rate like r to the minus d over 2, it's like, let's just try to get r to the minus 0.1 first. And then what you do is, so we want to drive the problem into the regime where the contrast is small, and then linearize. So you have to really split the proof into 2 parts. So the part that I wanted to explain is how we use the quantities that I defined in the last hour to actually kind of go up the scales and do a little kind of baby renormalization that at least gets us a rate of homogenization, even if the homogenization rate is bad. Because the rate will be bad, but after that, you can, because you're sort of in this, this linearization regime, you can then accelerate again. Okay, so that's the idea. If I can talk. So we're going to talk about how to prove a rate for these guys. So you remember that this thing is the matrix or the quadratic form. E maps to mu of this cube E, which was minimize over W in affine with slope E plus H10. So affine boundary data with slope E. The energy per unit volume domain. The energy per unit volume of the solution of the Dirichlet problem. Okay, I've written it. Okay. Right. So we have this. We saw that it was sub-additive. So in terms of the matrices, what that would say is that this is bounded by the sum over the small scale guys on the smaller grid. So I'm going to sum over lattice points in the smaller grid, which are contained in the big cube. And I'm going to put a slash in my sum again because I'm going to average. Okay, so slash sum, or yeah, sum slash. So we had that. And this is like telling us that we're bounded above by the arithmetic mean, but we don't have a way to control the other side. Okay, and that's bad. So we need a way to control the other side. And I mean, what we want to do is we want to prove that this converges to a bar with a rate. But it's very difficult to get information about this. And there's a very good reason, because this is defined in finite volume. You're at a specific scale, and this is defined at infinite volume. So if you try to get a rate, if you try to like get a bound on this directly, you're not going to succeed. You shouldn't do that. It's an inappropriate thing to do. Okay, so instead, okay, what you should try to do is get a bound on two successive scales. And if you can get a bound on that, perhaps you could kind of telescope over the scales and get the bound that you wanted in the first place, right? Because you can write a telescoping sum. So if we could bound this, we would be in business. And but the sub-additive ergodic theorem proof that we had before, you remember how the proof worked? We said, wait until the expectations of that had converged, and then you can control the fluctuations from that. But wait until the expectations have converged does not sound very quantitative, right? I'm pretty sure that a monotone function can converge at any rate, right? In fact, the modulus of convergence is a monotone function. So we need a way to control the expectations. So the whole game is to control the expected value of these guys. Control this. I mean, we know that this is going monotonely. It's increasing or it's decreasing down to a bar, but we don't know a rate for that, and we have to figure out a rate. And it's because we only have a one-sided bound here, and that's really hurting us. And so, what you have to do is you have to define the quantity that gives you the other side. Okay, so there's another quantity. Okay, which is going to have the inequality for the other side. So there's another quantity which we call A star, okay, of U. There's another way to define the coarse grain coefficient field. And this guy will have the other inequality. Okay, so that's good. And moreover, this guy will be less than the other guy. So if you want, and if they're equal, then that's telling you homogenization has happened. Okay, so in a sense, instead of looking at one matrix as being our coarse grain field, if you haven't homogenized yet, you need to have some uncertainty. So the correct way to say what is the coarse grain field at a finite scale M is, well, it's not really making sense to define one coarse grain field. I kind of have to let it be anything in that interval, where you understand that I am talking about matrices. I mean, in the sense of the matrix order, anything between these two. Okay, so that's what it's going to be. And this guy will satisfy the other inequality, and this guy satisfies that one. So together they kind of see both sides of the harmonic mean inequality. And I'm going to prove homogenization by showing that these guys have to squeeze together. Okay, yes.
Sorry, what you were saying, matrix is smaller than other, I was thinking about, yes, in the matrix order, but that you actually mentioned it, I had doubts. It's the what you're talking about is the symmetric.
Yeah, I'm doing the symmetric case.
Yeah. Okay. So it's like the positive definite smaller than delta thing.
Yes.
Okay.
Okay. The non-symmetric case also works, but it requires more notation. Okay. So let's just stick to this. Okay. So we're in the symmetric case. So that's So all these matrices are there's an ordering. Okay. Right. So the way we prove homogenization then is we study the gap between these two and show that the gap squeezes. And once the gap squeezes together, you can sort of prove everything. Okay, so let me tell you what this quantity is. So it's another sub-additive quantity. And so what other sub-additive quantity could there be? Well, we can define it like this, mu star. So I'm going to now use a dual variable. So before I was using E all the time, and now I'm going to switch to P and Q because they're kind of dual letters. So instead of writing E, I'll write P. This one's Q. I don't have a good letter that's dual to E. So I'm going to define this quantity. And this quantity is going to be this. I integrate. Now I have to make sure I get the sign right. Q dot the gradient minus the energy, U. And so I want to soup because the energy has a minus sign. And I soup over all H1 functions. I have no boundary condition. Okay, so this is my quantity. So why would you do this? Well, because you're desperately looking for some other sub-additive quantity, and so you try to write this down, and you realize that this is kind of a no Lagrangian part, so it's not going to affect the equation. So the maximizers are still solutions. Actually, the maximizer is just the solution of the Neumann problem. So the maximizer satisfies the Neumann problem. Oh, let's see. So I'm going to mix the letters up. I'll call this one V. The normal, so in with the arrow is the normal derivative at the boundary. Dot the flux should be the same as in dot Q at the boundary. So it kind of has affine Neumann data. I hope I did that right. I know that Jean-Christophe would tell me if I did. It's good. Okay, so this tells me that like my sort of Neumann data at the boundary is affine. Now, because there's no boundary condition, the way that I saw sub-additivity before was by gluing things together on the small scale. But I have no boundary condition. So how is this thing sub-additive? Well, it's sub-additive because you can restrict, you can slice it. So you look at the big scale maximizer, and you say I can restrict it to the smaller domains and test their maximization problem. Their maximums have to be bigger, and therefore you get sub-additivity instead of by gluing, you get it by cutting. So you get that this is less than, I have a slash here, so it's going to be the sub-additivity with weighted by the mean of the thing, UIQ. Okay, so I have sub-additivity again. Now you may think, oh, but this is not good because now you have two sub-additive things, but you wanted a super additive thing, right? Like, what are you doing? You should be making the inequality go the other way. But actually, that's because this is the quantity for A inverse, not A, which is why we're going to see that it satisfies the harmonic mean inequality. So can anyone tell me what that looks like? That you wrote the energy, instead of writing it in this quadratic form, you called it L for a Lagrangian. Okay, and then you had like Q dot this minus this. And then you were like, and say that you were like souping over this argument. Does that look like something? Yeah, so this is kind of, it's the dual quantity. We put a star here, but it's dangerous because it is not the convex dual function of the mu. Okay, actually in the limit it is, and you quantify homogenization by how much is it not, or how close is it to being the convex dual function. So, but you still have, it still satisfies the Finchel inequality, which I'll write in a second. So this is supposed to be the Legendre-Finchel transform of or kind of look like it. If I could put the soup kind of, instead of souping here and using the same function here, if I could just use any vector field here, then it would look like the Legendre-Finchel transform inside. But I'm constrained to use potential fields here. So it's gonna make it different. Okay, but we still write that this thing is given by a quadratic form, and you can, yeah.
Over in the female of the original A, I forgot. The H0 there, is that mean zero or is that
zero boundary data? Because I'm pinning it to the affine at the boundary. Here, there's no pinning at all.
So there's no, it's not the mean being zero.
There's no, I mean,
no up above. You couldn't put the, you couldn't.
No,
you could not
no. It has to be affine. Yeah, yeah. So this thing is quadratic because this thing is going to be linear again in Q. This is linear in Q. So this is a quadratic energy. So it's going to be quadratic in Q. And you'll find that you can make a matrix for it. And so we decide to call that matrix A star inverse. Okay, so that it's just the name we give to the matrix, which is this guy's quadratic form. We call it A star inverse. Okay, now the reason we call it A star inverse is because it's going to be this A star. Okay, okay, so now let me press the button. Okay, I'm going to have to do the proof that these converge tomorrow, I'm afraid. Okay, so these guys play well with each other. One guy sees one inequality, one guy sees the other inequality. So if they would be the same, you would be in good shape. Now, this guy's sub-additive. So if you write down the sub-additivity, what you get is that A star inverse is sub-additive. Okay, and this means that when I do the, if I take the inverse now of both sides, that I get this, take the inverse of both sides, it flips the inequality around. And I kind of get that A star on a big guy, on a big scale, is bounded below by the sample harmonic mean on the small scale. So it exactly sees the missing inequality, right? Because that's good. So in particular, if this would be equal to the other one, I would have both, and then I would be good. Okay, so we're going to use these together. They're both monotone. You can't really get a rate for one without the other. You have to get a rate for both together. Let me say one thing about a few more things about them, and then maybe I'll do the proof of convergence tomorrow. This guy allows any boundary data. So you're allowed to test that guy's minimizer in here. You can do it. Now, this guy's minimizer has affine boundary data. So I know the spatial average of its gradient is exactly the parameter E by the Stokes theorem, right? Because if phi is in LE plus H10, then this means that the gradient of phi is E after you average over the whole thing, right? By Stokes theorem. Okay, so if I test that guy in here, this is just Q dot E. I'll now use P. So I have that mu star of UQ is greater than what I would get if I just blindly plug that in. This term becomes Q dot P. And the other term is the energy of that guy, which is also called mu. So I have, except there's a minus sign. So I have minus mu of UP. And so I can write this on the other side as this. This is the Finchel inequality. It says that this is suggestive, right? If we knew that for a large domain U, for every P, I could choose a Q that made this equal, then they would be dual to each other. And that would actually tell you that the matrices are equal, right? Because this is, let me rewrite this now with matrices. I'm always cycling back and forth between the two notations, but here I have 1/2 P dot A of U P plus 1/2 Q A star of U Q greater than inverse greater than P dot Q. Yeah, so if for every P there was a Q which made this equal, then you can with just taking the derivative in Q or something, you see that these matrices are equal. Okay, so our plan is to not try to compare the A to A bar and not try to compare the A star to A bar, but to try to compare one to the other and to show that their differences has to shrink as we go up the scales at some rate. And if I can get them to shrink at some rate as we go up the scales, that will give me a convergence rate for both. Okay, so that is what I'm going to do next time. So maybe I will stop now for questions.
Yeah, thanks. Any questions for Scan?
What's the rate of convergence?
Well, it's that GFF thing. We prove that, I mean, in the end, we get that the corrector field converges to the Gaussian free field. The rate for these quantities, so I'll say more about this tomorrow. So when you first do the iteration, you're doing an iteration it's like it's like a decay of oscillation iteration. You show that as you go from one scale to the next, the difference between the two has to contract by some number less than 1. You iterate that, you get some algebraic rate of convergence as you go up. Usually when we do arguments like this, like in the proof of DeGiorgi's C alpha estimate, you do a decay of oscillation as you go down. Here we're going up. Okay, so you get some tiny exponent alpha. Once you have the alpha, that allows you to prove other things, which allow you to go back and then improve the alpha. And for these quantities, the optimal rate should be exponent 1. So it should be that a of this cube is minus this cube is less than c 3 to the minus m. And okay, so this is not quite right because this is a random variable. Okay, but this will be true for example with Gaussian tails. Okay, so this is what the proof gives for these, and that's sharp. And the reason it's sharp is because if you compare the Dirichlet and the Neumann, they're going to be different in the boundary layer. And the boundary layer already is going to make the solutions in L2 be apart by the square root of this. And this difference will be by the quadratic response to energy to a perturbation at a minimizer, the square of that. So it'll give that. Okay. And what that's telling you is that when you coarsen with these cubes, it's too rough because you're having too sharp of a cutoff. The cubes are convenient because they partition RD, but they create, because you suddenly have a sharp cutoff. I mean, even if you had white noise and you tested it against that, the variance would be that, not the CLT scaling, because I guess a white noise, I don't know about white noise, but if you had a finite range field, that it would do that, okay? Because you would see
That's not good.
Okay, yeah, I knew that I had my lawyer sitting here actually. That's the problem. Okay, so yeah, so you would actually see this sort of boundary layer come into and mess things up. Okay, because it's like things at scale 1 are entering in. So what you have to do to fix it is just to find the coarse grain coefficients with respect to a heat kernel, because a heat kernel also partitions, right? I mean, or at least one heat kernel is a sum of smaller heat kernels by the semigroup property. So in a sense, it's like you can break a cube into smaller cubes. You can break a big heat kernel into smaller heat kernels, and so it's a convenient way to partition as well. And the heat kernel doesn't have this boundary layer problem. So if you use the heat kernel, then you get a of a heat kernel at time t. So you plug a heat. Now I'm not even plugging in sets. I'm plugging in functions. But I mean, like you kind of make the boundary kind of smear it out. Then this thing lives on scale square root of t. So it's like square root of t is like 3 to the m. And this one you'll prove converges like, minus a bar. This one's going to converge at the CLT rate. So it's the square root of t to the minus d over 2, because this is the length scale of that function, and this is the CLT scale. So you'll get that. And this is telling you that you converge to white noise, and then a corollary is the Gaussian free field. So that's the eventual program. Now, writing down the whole proof of that takes like 100 pages. It used to take 250, but now we're got it down to 100 pages. But you just have to have, I mean, there's a lot of triangle inequalities that you have to do, right? I mean, that's what they say about analysts. Like an analyst is somebody who just is like unwinding consequences of the triangle inequality. But there's a lot of triangle inequalities when you're. Sorry for that long answer to your question. But
can you say something about, so for this dual quantity, can you use this to study like also a soft homogenization problem? And
yes, I could have, if I wanted to, have used this instead of the one that DeGiorgi proposed from the beginning, and it would have worked.
But that's still to solve like the homogenization Dirichlet problem, even though
this would homogenize the Neumann problem.
Okay, so
and you would get correctors in finite volume, which are not the same finite volume correctors I had before. They solve the Neumann problem instead, but they still work the same way. It's fine. Okay, so you could have used this. It's just that this is harder to think of, right? Yeah. So when DeGiorgi was writing in his paper from 1972, he anticipated this multi-scale, scale-to-scale. What he didn't anticipate was this quantity, and he wanted to prove all these inequalities just with the one quantity. That's what they were. That's what seemed like in his. I mean, this is. I'm reading a lot into like this much text at the bottom of this paper, but that's what it looks like to me.